take a look at this one. Say I've got f of x equals x squared minus 7x plus 12 over x minus 3. Well, if we look here, we might, and well, let's ask this. For which x is there a discontinuity in this graph? Where might we should look? Obviously, probably at 3, right? The denominator here is not defined at 3. I mean, the denominator is 0 at 3, so the function is not defined at 3. So that's probably a good place to look for discontinuity. And yeah, x can't be 3, so we're going to have a discontinuity at 3. But here's what I wanted to point out. If we look at the graph of this, take a look at the graph of that. One thing about it is, I may have pointed this out to you before, but on this one, x squared minus 7x plus 12 divided by x minus 3. Okay? Looks like it's just like a straight line. However, we do know at 3 there is a discontinuity. The denominator can't be 0. And so what I've got there is, yeah, there is a break right there. Usually, if we draw it, when we draw the graph, yeah, we're just going to put a little circle right at the 3. X is 3 mark. And there. Now, how would I explain, using the definition of continuity, this discontinuity at 3? How would I explain that? Well, it's, you know, that's the 3-part definition, 3 parts to the definition. What you've got, you've either got, or you got to have the limit as x approaches a exists, the function value at a exists, and then the two are equal, right? Those are the 3 things. Now, which one falls through here? The limit exists. Limit does exist. But as we were saying, the function value doesn't exist, and that's or doesn't have a value. Okay? Okay. All right. So anyway, that's what we did before. Let's look at this one. It's basically the same function, except I'm going to make it a piecewise. We're going to say f of x is that x squared minus 7x plus 12 divided by x minus 3, but only if x is not equal to 3. Okay? If x equals 3, I'm going to say function value is negative 1. Now, the question is there still a discontinuity at 3? Well, let's check it. What's the limit as x approaches 3 now of my f of x? We didn't do it a while ago, but it does exist. What is it? Well, it'd be the limit. Since I'm approaching 3, I'm using this, right? So it'd be x squared. It'd be the limit x approaches 3 of x squared minus 7x plus 12 divided by x minus 3, which I can do that one just by a little bit of factoring. X minus 4 times x minus 3 over x minus 3. X squared minus 7x plus 12 factors that way. Take out the 3. X minus 3's. What's left? Looks like the limit is x approaches 3 of x minus 4. What's the limit of as x approaches 3 of x minus 4? Well, I can substitute in now, can't I? It'll be 3 minus 4, which is negative 1. Okay, now what's the function value at 3? Well, unlike before, I do have a function value at 3 because now I've kind of put something in at 3. If it was just that, I wouldn't have a function value at 3. But now I do have a function value at 3. What's the function value at 3? It's negative 1. So do you see now we've got continuity? Because these two, so the last part is these two are equal, and they are, aren't they? So it's not discontinuous. It is continuous at 3. Now it is continuous at 3. There's no, in other words, if I draw the graph here, okay, what I've got is, I've got that same graph I had before. This part, I've got that little circle, but now turns out I fill that in. So I don't have that jump. Okay? All that to say this. Some graphs have what are called removable discontinuities. This is one. This is the original function was this. I can remove that discontinuity at 3 by saying the function value is negative 1 at 3. I can do that. That's called a removable. If you can do that to a discontinuity, it's called a removable discontinuity. So for f of x equals x squared minus 7x plus 12 over x minus 3, there's a removable discontinuity at x equals 3. And to remove it, this is what I do. Okay? Just define it to be negative 1 at x equals 3. Okay? With me on that. So we've seen a couple of examples of those. Okay? So a removable discontinuity is just a discontinuity you can remove by defining a single value. Okay. Now, are all discontinuities like that? Well, no, because what if I have f of x equals 1 over x? I'm sort of in the same boat as I was with the previous f of x, but first of all, what's the discontinuity here? X equals 0. Okay. It's discontinuous at x equals 0. Is that one removable, though? Can I say, well, x is this at x equals 0, or the f of x is this at x equals 0? Well, the answer would be no. Okay? It's not removable. It is not removable because of what happens at x equals 0. At x equals 0, and what happens to your limit as x approaches 0? What is the limit as x approaches 0 of this f of x, 1 over x. Well, this one's different. This one's not a whole, is it? This one is an infinite limit, isn't it? The limit here is, as x approaches 0, is, well, it's on one side it's negative infinity, just looking at the graph here. On one side it's negative infinity, on the other side it's positive infinity, so the limit really does not exist. But even more specifically, they're infinities on one side and the other. Okay? And so when you have those type of discontinuities, because you've got infinite limits on either side there, that's not removable. Because I can't say this value is at x equals 0, that the function value is this, because, well, there's not really any values to say those could be. Okay? But for obvious reasons, we would call the discontinuity at x equals 0 an infinite discontinuity. Makes sense? Because, yeah, you've got infinity limits on either side there. Well, negative infinity and positive infinity. One other type. So that's infinite discontinuities. Removable, infinite, and it's a non-removable one. And then the other one is the one like we had earlier. F of x equals the absolute value of x. Again, we've got a discontinuity at 0. But that one also, let's look at it. Removable? No. No, it's not. Here's why. Because if you think about the limit as x approaches 0, what do we discover about that? Doesn't exist either, does it? Yeah, and if your limit doesn't exist as you approach that number, you can't remove it, because that's really what the removable is. You set your value equal to the limit. Here, this limit doesn't exist, right? Because, well, we verified it directly, and looking at the graph, it's coming in at two different levels. The limit as x approaches 0 from the left is negative 1, and the limit as x approaches from the right, 0 from the right, is positive 1. So the limit doesn't exist. They come at two different levels. Okay? So you can't remove that. If the limit doesn't exist, if the limit is infinity, either way, you can't remove those. So those are non-removable. Now, like this one is infinite. This one's not an infinite discontinuity. It's known as, well, if you look at if you take a look at the graph here of the absolute value of x over x, it was that. And so in those cases, for good reason, at 0, you're said to have a jump discontinuity, because it jumps at 0, it jumps from one value to another, so to speak. Okay? All right. Okay. All right, so I wanted to mention that to you, and then also talk about the one-sided continuity also. A function f is continuous from the right if the limit as x approaches a at a function f is continuous from the right at x equals a if the limit as x approaches a f of x approaches a from the right of f of x equals f of a. Function f is continuous from the right at x equals a if the limit as x approaches a from the right equals f of a, equals the function value at a. And then similarly, function f is continuous from the left. Just reverse that, or change it to the limit from the left. All right, so function f is continuous from the left at x equals a if the limit as x approaches a from the left is function. Okay? All right, here's what that means. Graphically, here's what it means. Let's say I've got function f here. All right, and I'm going to have a discontinuity. I'm going to go here, and then the other one's going to be here. Well, obviously I have discontinuous, and let's say that's 2. Obviously here I have discontinuous at 2, don't I? Discontinuous at 2. However, it's continuous from the right at 2. Do you see why? Based on this right here. What is the limit as x approaches 2 from the right? What's the limit as you approach 2 from the right? Well, it's up here. Let's call it 3. Isn't the limit as you approach 2 from the right 3? Okay, what's the function value at 2? Well, the function value is 2 because of my filled in circle there. Isn't the function value at 2 also 3? So there you go. That's what we're saying. If the limit from the right equals the function value, it's continuous from the right. And so you can you come up with a graph here for this one? Continuous from the left, it would be exactly the opposite as far as this point is concerned. I'd have, let's say I'm coming in here, let's say at 3, all right, so it's coming in, and the graph comes in, and then it's closed circle there at 3, and then whatever on this side. That's continuous from the left, isn't it? Because as you come in from the right, you're coming up here, but the function value is down here. So it's not continuous from the right, because the limit's up here. But the limit from the left is coming into this value, which let's call it 1. The limit's coming in at 1, the function value's at 1, so that's continuous from the left. At x equals 3 for that one. All right, so that's the idea. All right. So let's get give you one here. F of x equals 2x for, this is piecewise, 2x for x is less than negative 2. It's x squared minus 1 for negative 2 less than x less than or equal to 2. And then it's minus x plus 4 for x greater than 2. All right, so obviously here I have some discontinuities. Where's this one discontinuous? Well, probably there at the brakes, right? It's discontinuous at probably negative 2. How would I verify that, though? Well, I need to see what the limits from the right and left are. If you limit x x approaches negative 2 from the left, limit as x approaches 2 from the negative 2 from the right. Well, negative 2 from the left, that would be this one. It's 2 times negative 2, which is negative 4. Negative 2 from the right would be this one, so that would be negative 2 squared minus 1, which is 3. Yeah, so there you go. It's discontinuous because the limit does not exist at negative 2. Okay, so it's discontinuous there. And then at x equals 2, also discontinuous at negative 2. How about positive 2? I think so too. It's discontinuous at x equals 2, same deal. Limit as x approaches 2, f of x from the left would be this one. 2 squared minus 1 is 3. The limit as x approaches 2 from the right, 2 from the right is the greater than side, so it'll be this one. So that'll be negative 2 plus 4. Hey, that's 2. Okay, so the limit does not exist, so it's discontinuous. Therefore, because to be continuous, the limit has to exist. And it does not, so it's discontinuous. Okay. With me on that so far? All right, but what we're talking about now, though, is part 2. At those discontinuities, can you say it's continuous from the right or the left? Well, we've got, continuous from the right or left has to do with the limit from the right, limit from the left, and the function value for that particular value. So I've got, let's start with negative 2. At x equals negative 2, I've got the limit from the left is negative 4, the limit from the right is 3. So all I need to do is see which of those matches up with the actual function value. What is the function value at negative 2? Well, the function value at negative 2, looking at my parameters there, where would that fit in? Where would I go for x is negative 2 equal to negative 2? It'd be this one, wouldn't it? X squared minus 1. So f of negative 2 is negative 2 squared plus minus 1. Which is 3. All right, so f of negative 2 is 3. Which one of these does it match up with on the limit? Matches up with that one, which is the limit from the right. So it's continuous from the right at negative 2. With me on that? Continuous from the right at negative 2. All right, so let's check at positive 2. Well, again, we've got the limit from the right and the left at positive 2. So let's just see what the function value is at 2. What's the function value at 2? Well, again, it's the equal to 2 that I'm looking for. So again, it's the x squared minus 1, which is also 3. Which one does that match up with as far as the limits go? It matches with the limit from the left.